Hello everyone, it's Ting here introducing the WEAR project. As you may wonder, what is WEAR? WEAR stands for Wearable Electromyography Analysis for Rehabilitation. Alright, let's get into it. So it's time to introduce my team. My team members includes Kuwar, myself, and Maninder. Kuwar is responsible for the systems, software, and as well as the final PCB design. And I am responsible for the BLE subsystem, the electrodes, and as well as all the marketing for the project. And finally, Manny takes care of the mechanical aspects of the project, as well as the SD subsystem. As you can see, the WEAR project consists of both mechanical and electrical aspects. Also, I wanted to thank our project owners, Dr. Chang from Carleton University, and as well as Dr. Lamar from the Ottawa Hospital for all the insight and time they have provided for our project. We wouldn't have made it this far without their help, so thank you very much. Here's the agenda for today. I'm going to cover the Wear system overview as well as the Gantt chart showing the progress of the project and as well as the project original and revised scopes. Then Kuwar will go over the details of the software and as well as the hardware progress of the project and the final designs and the PCB schematics. Lastly, Manny would go over the mechanical aspects of the design and how the final mechanical enclosure came to be. Also, how much it will cost to manufacture the product and as well as the current expenses thus far. This is the Wear system overview and how we envision to eliminate the traditional methods of taking a EMG measurement. As technology gets more advanced nowadays, accessibility is crucial into the development of this project. We wanted to create a device that is wearable and smart for our user, as the initial concept was developed by master student Adam Freed. The Wear system allows measurement of EMG to be measured through an array of electrodes. Then, taking those measurements, the system is able to process the collected data with our main controller, the ADS-1298. Furthermore, the data is sent to the microcontroller for an option to visually stream the collected data via Bluetooth with an app, or the option to store the data to the SD card so that the user could then take the data to a certified physician for further analysis. Here is our Gantt chart showing the progress of the project. In late August 2019, the project was familiarized from the 2017-2018 group. Then the team came together during September and began to do our initial research for the project. Moving on to October, we were able to base our design with our research done in September. In November, the team were able to pick out the minimum requirements and as well as the materials needed for the project. Going into December, the team started to order parts and began to do the basic functionality test of each subsystem. After successfully testing each component of the system was finally integrated into its final design in January 2020. Then in February, the final PCB was made and sent to our manufacturer. Then in March, the system was fully complete in order to close out the project. However, because of the pandemic, the project ended during April. Fortunately, the team were able to complete the scope as promised to our clients. This was the original scope agreed with our client. The scope consists of a rechargeable, user-friendly, wearable device that would acquire and log 8 channels of data and as well as 2 channels of visualization via Bluetooth. The final product would be a 2-layer PCB design and of course a repository to document project. During the project execution, some changes and additional features were added to the scope in order to improve the overall design of the system. We had to make some compromise with our PCB design as a 2-layer board would be too difficult to produce with the components we have. Therefore, the client has agreed to a 4-layer design. Then a touchscreen was then added to the design with an on-board oscilloscope and graphing capabilities. A 9-dot orientation sensor was also incorporated into the design as it would provide useful information for our measurements. Finally, we also designed a mechanical enclosure as the housing of the system. Now my friend Kuwar will take over and discuss the details of the wear system.
Thank you, Ting. I'll be taking over from my colleague Ting-Chieh in order to explain some of the more technical aspects of this project. So this is an AFE analog front end made by Texas Instruments. It's the ADS1298 package. It's the chip I see right there. And all it is 8 differential amplifiers that feed into a digital controller. So eight differential amplifiers take in 16 electrodes, two electrodes per channel, or 2 electrodes per differential amplifier. And the digital controller on this thing takes the data from those all those 8 channels and packs it into a 24-bit A to D converter. So it'll convert all those channels into 24 bits. 24 bits times 8 is 192 total bits. It'll pack it into an array as well as add another 24 bits for a status header, and it will send it over SPI. So our task was to connect this AFE to a microcontroller, be able to decode that data, stream that data across Bluetooth, BLE 4.0, so a user can visualize and see it, as well as save it to a micro SD card for later pulling it for later post analysis by a doctor or medical professionals. There's also an IME initial measurement unit involved, which tracks the hand motion, like how the human arm or leg or whatever area of the body that you're tracking, how it moves with correlation in or conjunction to the electrodes or EMG signals. As you can see, so our data acquisition process was not easy. This is a circuit here, right here, and it ties to the AFE, which is right here. And we had to update quite a bit of the software and edit some libraries that wouldn't work with the 2000 the new controller that we chose. We had to fix some buffer overflow issues, which took quite a bit of time, but we were successfully able to talk to the AFE in the end and acquire data from all individual channels, and we were able to select which channels to turn on, off, change settings right directly to the registers. For a microcontroller, we chose the Ting-Chieh 3.6. This is an ARM M4 Cortex. And the reason we chose this microcontroller and why the previous batches or teams got stuck is because the micro SD card uses an SPI interface to save data. So does the AFE. Most if not all, actually all Arduinos have only just one SPI bus, which means that bus has to be shared between the AFE as well as the micro SD card, which creates problems because the controller has to acquire data from the AFE, stop listening to it, write to the SD card, stop writing to the SD card, come back, start listening to the AFE. This creates a lot of timing problems, especially when you step up the sample rate. So that was quite a bit of challenge to fix. So we went with this controller, which has 3 separate SPI buses. We only use 2 in this case, and one of them is a dedicated SPI bus for a micro SD card to just save data. So the controller can just acquire data right to the micro SD card unconditionally. Now, in order to test this device or make sure that what we were measuring was actual EMG signals, because EMG looks a lot like noise, we had to create a specific test, which I designed to show a client or to make sure that we are actually measuring the signal we are measuring is actually EMG. So what we did was we used the MyDAC as a function generator. It has 2 channels. We generated various functions about 0.1 millivolts to 0.2 millivolts, peak to peak. And those signals were fed into the electrodes array here. The AFE picked up those signals. Then the signals were sent over SPI, encoded by the AFE and sent over SPI to a microcontroller. And the microcontroller plotted those signals on the Arduino serial plotter. So what this does is, if I am generating a known signal, like a sine wave, a square wave with known parameters, this should match the graph or the plot on the serial plotter, which confirms that whatever we are measuring from the AFE is actually EMG. Next, I can show you some of our results that we did. So this is the proof of operation. what you see here is straight from the Arduino serial monitor. I was generating a 2 Hz sine wave here on the MIDAC, and as I showed previously, the AFE picks it up, sends it over SPI to the microcontroller, and the microcontroller plots it. So this is at 2 Hz. This is a square wave. We have other pictures of triangular wave, etc. Now, we have to get it, in order to actually get usable data, we had to step it up to get 50 to 100 Hz because that's the range EMG traditionally works in. Goes up to a maximum of 300 Hz. So we need a little bit of more additional testing in order to confirm that it works. But this is an image of 500 samples per second. As you can see, it's very clear. Fortunately, I have no control over the side axis, so it can't get much clearer than this, but this is a 50 Hz signal generated by the MIDAC, which is picked up by a microcontroller. And this is a 100 Hz signal. So as you can see, it's lossless. There is no drop in data points, or like there is no buffer overflow issues, nothing. It's very clear. So we were able to achieve this successfully. This pretty much proves that the AFE actually talks to a microcontroller properly and is able to test and pick up a known signal. And we were also able to save the sine waves and square waves onto a micro SD card, which I'll explain in the next slide. So for data logging feature, we have a micro SD card. It shows 32 gigabytes. There's calculations that were done that show that this micro SD can record like up to 40 days if need be. But this is what it saves on the micro. This is what the data looks like. So that's your 216-bit array converted to hex. So in hex, it becomes a 55-byte array. And the first 6 bytes are a status header. This is just basically a status header is something that shows that the system is actually functional, active, the status of different inputs and outputs on the AFE itself. And this is the data, along with a timestamp. So as you can see, every data or every sample comes saved with a timestamp. And every 6 bytes corresponds to a single channel. This is done successfully. The other part of the project was also getting data from a IME Fusion Sensor. So we went with the Bosch BNO055 based on client recommendations and some additional research that we did. So as you can see, this data file right here saves XYZ axis, as well as the timestamp, as well as the accelerometer, magnetometer, and gyroscope values. This needs to be calibrated, but it saves this data in conjunction or in parallel with the previous data that we just showed you. So the system also works successfully. With this, a user can actually plot hand motion or leg motion or any motion of the human motion in parallel with the EMG signals. This is very useful in areas like kinesiology or gait analysis. Now I'll explain a little bit about Bluetooth, BLE 4.0. So this is the module comes from Adafruit. It's based on an NRF 51822 chip, and the problem with this module was the library limited it to 9600 bits per second. But in order to send 2 channels, which was in our scope, we needed at least 48,000 bits per second. So it was initially a challenge to change the baud rate because the library itself limited it, but I had to learn a little bit of object-oriented programming, modify some of the classes, and I was able to successfully change the baud rate of this module to 115200 in order to get 2 channels off without any lags. So pleased to report that we actually successfully achieved 2 channels, and this is what the EMG looks like. This is a single channel EMG. Show you 2 channels. So that's a single channel. That's 2 channels, 2 separate channels generated by the MIDAC, picked up by the AFE, sent to the microcontroller, and the microcontroller plots this or sends it over Bluetooth. So my cell phone or an Android device or even a PC capable of Bluetooth can plot it. Now, for data visualization, or to prove that the data that we saved on the micro SD card is actually legitimate, I built a Python script. This is not part of the scope, but in order to show visually that it is actually what the data generator is actually saved properly, I had to write a code in Python in order to take that notepad file or the data and reconstruct a graph. So this also proves that we are not only able to save data to the micro SD, but even recover it and plot it for post-analysis done on my PC. So those are all 8 channels. It doesn't show here, but we are successfully able to generate sine waves and square waves as well and save them here. Next, I'll briefly explain the schematics of the project since we have a PCB coming up. So this is schematics for the power section. The AFE needs 3 voltages, positive 2.5, negative 2.5, and 3 volts, which comes from the microcontroller. But the other 2 voltages had to be generated using specific ICs. And there's a fourth voltage, 5 volts, for the RGB indicator or the LCD screen to work. So I had to use a boost circuit here in order to get the 3.3 volts to 5 volts. This is the schematic of the microcontroller and the other subsystems. So this is our microcontroller, it's the BLE module, and this is the motion sensor, IMU. It's not the motion sensor, sorry, the initial measurement unit. These are 3 buttons for 3 different modes that correspond to 3 different modes that a user can pick, and that's our power switch. Now for the AFE itself, the complicated one, that's the ADS1298, and this is the electrode array, which ties into just a jumper or header for testing. So we had a sort of crazy idea where instead of having 16 electrodes come out of this device, we would have just one unit or one wire coming out. So this is the idea. We used HDMI. HDMI has 19 usable wires, and we only needed 10 basically based on Adam Freed's research. So this is the schematic of what it looks like. That's a microcontroller. This is the digital controller, 8 op amps, differential configuration, and that ties to an HDMI port, which we picked a male to female extender cable right here. And ideally this part would tie here into the device. That's the cable, and this is the female portion, which would tie into this small device right here. It's a breakout board for HDMI. And what happens is you can plug the female cable right here and have all these electrodes just break out, come out of this unit nicely, and tie into an electrode sleeve that Adam Freed initially designed, which is also part of the project. So that's how we even tested this. It worked successfully. So HDMI is actually a good option. Ideally, we would be with micro HDMI, but we were not able to find proper breakouts for micro HDMI. So this is what it would look like. Now the PCB aspect based on these schematics was a big challenge because we had to build a 4-layer board. All those components, there's roughly about 130 components on the board, so it's impossible to do on a 2-layer board. So that was day one. That was the task that I had to place all these components on this. Slowly, I had to learn how to do all this across a 4-layer board. In the end, it ended up looking like this along with dimensions. And so the PCB routing was a big challenge since it's a 4-layer board. I had to hand route all. I couldn't use auto router because Eagle's auto router is not competent enough for a 4-layer board. So it's all the 4 different layers of the PCB that turned out. So the design was basically the top layer was just the analog front-end routing. The last layer at the bottom was digital signals from the microcontroller, routing from the microcontroller. The middle 2 are power and ground as a full ground plane that segregates both the microcontroller as well as the analog front end. So it cancels out noise. There's no very minimal noise on the board, and they both have separate grounds. So I had to separate analog ground and digital ground. These are just some 3D PCB renders that we did. So we pushed the design to Fusion, and in order to get a better 3D idea, and then design the mechanical enclosure around this PCB, which now my colleague Maninder Singh will explain.
Hello everyone, my name is Maninder Singh. Being the only mechanical student, my primary role was to develop a mechanical enclosure for the electric system. And I was also responsible for initial source code of SD subsystem as well as maintaining budgets of the project. So enclosure designs of the electric subsystem were embedded within a mechanical enclosure. The enclosure were designed on SolidWorks, that is CAD software. Initially, 2 approaches were made for the design, one with the LCD touchscreen, another with the RGB ring indicator. First approach had an LCD touchscreen on the top of the body, which made it attractive and user-friendly. Different modes can be selected by simply touching the screen. An inbuilt oscilloscope can be used to see live EMG signals. The second approach was with an RGB indicator, which different modes with the help of the buttons shows different LED lights turned on, and each light indicates the functionality of the individual mode. The base was kept same for both the approaches, but two different bezels were cut and made to fit both the components, that is LCD as well as RGB, perfectly on top of the bezel. The advantage was that PCB was designed to implement either of the two approaches, hence it created a product line for the project. Our scope was to make a wearable device which can be easily tied around the human leg or arm or anywhere EMG signals are generated and measured. So for achieving the goal, strap holders were designed on the sides of the base of enclosure, which can be seen in the pictures. Velcro or rubber straps are used to tie the enclosure to human arm or leg, and electrodes are placed on the human skin. Velcro is preferably used due to no significant allergy found, and it is one of the cheapest way, and it is easily available in most of the Canadian stores. Enclosure dimensions are 150 mm in length, 70 mm in width, and about 30 mm in height. So the material used to 3D print the enclosure is PLA plastic, but most of the enclosures are printed with the ABS material as well. So M2 screws are used to hold PCB inside the subsystem, and M3 screws, that are the machine screws, tighten the screen to the bezel. And M2 machine screws of about 15 mm length assembles the bezel to the base. Vision versus the execution of PCB. On the left side is the 3D vision of a designed PCB with all the launching pads for different components such as Ting-Chieh, Adafruits, BLE module, 9-DOF IME sensor, push buttons and slide buttons. On the right side we have the printed 4-layer PCB. 3D render of mechanical enclosure are designed using Inventor software, and it can be seen on the left side of the screen, and on the right side you can see the printed enclosure. On top there is a laser cut glass layer on which the wear system wear is written and the EMG signal is made, as well as we have the AC logo on top of that. It makes this render look more attractive. Budget and current expenses. The budget allotted to the team was around $1,600, out of which team had spent around $1,400 on the project. So around $735 was spent on DigiKey, and around $400 was spent on Amazon. Around $220 is spent on PCB, printing and shipping, and around $55 is spent on the Adafruits BLE module. And you can see in the pie chart the remaining budget is around $153. So far we have spent like all the budget allotted to us. Challenges. So as our project was very interesting and technical, there were a lot of challenges faced. Hardware. The system was very complex with both analog and digital circuits. The ADS chip was itself very challenging to interface with the new preferred microcontroller that was Ting-Chieh, and many implementation to the code was done. PCB designs. Designing a 4-layer PCB was very challenging. With further routing of the PCB was very hard job. Testing of the system was impossible due to the complexity of the design. Software challenges. BLE subsystem. So knowledge of the object-oriented programming language is needed, as well as custom libraries and changes to libraries was done to change the baud rate of the BLE subsystem from 9600 to the desired one. Interfacing with the next-gen display. So for making the device more user-friendly, we added the LCD touchscreen as I told before. So for that we need complex amalgam of low-level coding as well as a GUI-based editor software. As this subsystem, there was a loss of data on the SD subsystem from the initial source code, so we need to add a buffer in the code which overcome that challenge.
So that concludes the Wear project, guys. Thank you so much for watching. And if you have any questions or comments or concerns, these are our emails below. Please feel free to contact us, and I'll leave a link in the description box below. Thank you so much again.